What I want to do today is talk a bit about some of the emerging technologies in silicon carbide electronics, and this is not going to be what you would consider a traditional power electronics presentation, because we're going to talk about a lot of the things that are at the very edge of what people are doing in silicon carbide power electronics. For the past, maybe 10 years, a number of demonstrations of power electronic converters and other types of conditioning circuits have been demonstrated using silicon carbide technology in an effort to demonstrate how it could be a game changer between silicon and silicon carbide, for example, in terms of higher frequency operation, higher temperature perhaps in some cases, and then of course for the whole idea of promoting higher power density. So what we're going to talk about today is some of the things that are beyond the silicon carbide powered device. What are the other things that we need to look at in order to make reliable and effective silicon carbide based power electronics? So I'm a director of a couple of centers. One of them is the Grid Connected Advanced Power Electronics Systems Center, GRAPES, and then another is the POET Center, which is an ERC, and some of the work that I'll talk about comes from those centers. And so I'll talk a little bit about that, but I won't really try to identify it too much. Some of it's grid, and the POET Centers focus more on mobile applications like electric vehicles, heavy equipment, and aerospace. So what I'll talk about are some of the, I'll kind of give a motivation. What are some of the driving factors for these emerging trends? What's making these things the most recent work? Why are they important? And then I'll talk about some of the things that relate to that. So some of wide bandgap IC design, for example, and wide bandgap circuits, and then also design automation. These are two of the areas that are really being driven very hard, because what we're able to do in silicon carbide today, we find there's this huge multi-dimensional space of things that needs to be optimized because we have this opportunity. But no one really has mastered how best to do that. And this is some of the things that we need to look at as a society. So I'll start with sort of a motivation as it relates to grid applications. The first chart that I have here talks about all the sources of energy in the US and how they're generated, whether it be solar, nuclear, hydro, wind, geothermal, all those different sources, and then how they feed into their end use. So that may be transportation, industrial, commercial, residential, and you have all of this electricity, for example, that gets generated. And the point of my slide here is basically to give you some idea of how that energy, oops, we need to put that in presentation mode, how that energy gets lost before it gets to its end use. So if you look at it, you're looking at 67% of the electricity generated never makes it to the end use. These are just US numbers, okay? So you can go to Lawrence Livermore National Lab's website and they'll have these charted for each year in terms of how much energy is generated versus how much energy is used. Now, I don't think I need to motivate any further the fact that if we inserted more power electronics into our electric power grid, we would have a higher efficiency use than we have right here. If we utilize perhaps more HVDC, we would have a higher efficiency than we have today. So there's lots of opportunities for growth in terms of power electronics in the grid area. Silicon carbide happens to be one of the technologies that applies very well to grid applications. If you look at electric transportation, and others will talk about electrified aircraft and so forth, you start seeing that there's a tremendous number of opportunities for more electric transportation. So whether it's trains or marine systems, aerospace, or cars and trucks. The Tesla truck was just announced a couple of weeks ago, okay? So, but it's not just propulsion. It's all the other systems that are involved in those electrified platforms that give us an opportunity for more electrified transportation. But the problem that you run into in a lot of these cases is the power electronics needed are too big to fit onto some of these platforms in an effective way. In fact, take something like a recent project that we're starting in January with Caterpillar. Currently, they want a dual inverter, and the current size of the inverter is 2 times 75 kilowatts. But what they prefer is 2 times 250 kilowatts, but it's too large to fit on the platform. And this is a heavy loader. But because of all the other equipment on the heavy loader, there's no room for the power electronics. Thus silicon carbide. You start moving up to higher frequencies and higher power density and perhaps even higher temperature operation just a little bit. You end up with a situation where you have a need for rugged electronics and a need for volume reduction. And once again, this is a perfect match for what we're doing in this field. So it's an enabler. So here's an example of a project that we did a few years ago with Toyota and a company called Arkansas Power Electronics, which is now actually part of Cree. And these charging electronics demonstrated in silicon carbide a 35x power density improvement over the state of the art. In fact, this device right here is about this large. And compare that to, he's holding the device right here, compared to the water-cooled version of silicon. This guy here was 1.6 kilowatts. This guy is 6.6 kilowatts. This is 98.5% efficient, air-cooled. This is water-cooled. So it has its own circulation loop just for the electronics, okay? This is why Toyota made the decision that in their 2020 model, they're going to silicon carbide in their cars, okay? This was going into a plug-in hybrid that was not even a commercially available car, but it was installed in the car, okay? And so, again, this was just one of those many demonstrations throughout the years that you've seen of the potential of silicon carbide. This particular converter is operating at about 250 kilohertz, as opposed to the 30 kilohertz for the silicon electronics, okay? So, of course, the passive shrink, the thermal management was much easier to develop because it was so highly efficient, and it had a very flat efficiency curve as a function of the amount of power. So, again, all this is just to simply motivate why silicon carbide in the first place. And so there's a lot of upside potential. So going back to the grid for the moment, just in terms of everyday use, these little white boxes you see here, all the power converters, all the different places in which power electronics may find itself. We like to say power electronics everywhere, okay? Well, in fact, you start looking at all the different applications, even things like appliances. These things really want to be DC, okay? They don't really want to be AC, they really want to be DC. And so as we start modifying the designs of these systems throughout the coming years, we'll see higher and higher efficiencies as a result of that. But in many cases, it's still, while you wouldn't think of it, it's still somewhat volume sensitive. If I can make for you a 50 kilowatt converter and put it in the palm of my hand, would you rather have that or one the size of this lector? Most cases, you'd rather have this size if it was reliable. If it's not reliable, who's going to care anyway? Okay, so it has to be reliable. So as a result, all of these are reasons why silicon carbide is, and perhaps gallium nitride in some lower voltage applications, are solutions that we have to start taking a very strong look at. And then my last slide on terms of motivation is you're all familiar with the Google Little Box Challenge that happened a few years ago. Here's the perfect example of where you have to be a little bit careful in how far you push things. This particular design, which was one of the finalists, was about 216 watts per cubic inch, very high power density, all gallium nitride based, and it lasted for 10 hours, and then it failed, okay? This one, which was not as high power density, okay, it lasted for 500 hours, and it's still going. You sacrifice power density sometimes for reliability, okay? And so one of the things that you have to be, but this is a trade-off that we need to be able to take advantage of it at the design time. We need to be able to master how to understand the reliability when we're designing the converter, not after the fact. You don't test in the quality. You have to design in the quality. And so this is a case where there's a trade-off. Okay, we're all part of the same team here, so that's why I'm discussing this. But this is a trade-off where you push the power density as far as you can, but you sacrifice reliability. And if you back off a little bit, you can still maintain the reliability. This particular one was a hybrid gallium nitride silicon carbide solution, but it also dealt with the thermal management much better, okay? So thermally, it did not have the issues, okay? So you have to deal with these. And so this is what, in fact, the Poets Center is focused on for electrified transportation, is the simultaneous design of the electrical and thermal. Okay, so it's a multi-objective optimization approach to the design. Okay? But the design involves more than just the power circuit topology and the controls. It involves other components, passives, the gate drivers, the protection circuits, all the other pieces. Any of the weak link makes the thing unreliable. So we have to address the entire scope of what we're building. And that's what I'll talk about today, is the rest of the scope. The key is heterogeneous integration. That's the key word. How do I put it all together in a way that I understand the reliability and I understand the performance and I can guarantee both? Okay? So, yes, certainly the semiconductor devices, those are an enabling technology. Everything flows from the new materials. Materials change the world. The Bronze Age, you know, all of this, the Stone Age. As the materials change, our world changes. Now we're in the wide bandgap age, okay? As we're moving away from the silicon age, okay? And the world will be different. And then there's all these other things that come with that. This is the top of the tree, or the root, and then everything else grows from those materials. So you have to model the devices. You have to manage the thermal, of course the electrical performance. This is where we live right here as power electronics people, but also mechanical performance. And then you start looking at some of the other issues surrounding it. We could call it the shrubbery around the power electronics if you want to take a power electronics centric view of it. But we need to look at how do we lay out the system in an optimized way to manage the thermal. And what about all those circuits that go around it to make it work? And then what about the passives? Often that can be the weak link. So I submit that to achieve the best performance out of wide bandgap device advances, we have to pay attention to the electronic packaging and the integration, this heterogeneous integration. We have to focus on the reduction of parasitics because we will be doing higher frequency operation to get the gains that we seek, higher efficiency, smaller volume. We have to pay attention to thermal management, and of course, if it's not reliable, nobody's going to care, okay? And then finally, it's going to require advances in the materials for the packaging and the packaging processes. How do we manufacture this in a low cost? And then, of course, the design tools. So these are things that we have to begin to pay attention to more than we have in the past as it relates to even silicon electronics. Because of the way we've designed silicon electronics, we've not had to concern ourselves as much with the confluence of all of these issues all at once. But now they're all coming together in an integrated way. We have to begin to pay attention. And it's simply because, right here, higher frequency operation is bringing this into play. We have to start considering things that we hadn't looked at before. So I'm going to show you just a few examples of some things that we've had to look at as it relates to both high voltage and then high power density. So we've developed new materials for 10 kV breakdown so that we can package these wonderful high voltage devices made in silicon carbide, okay? So new attach methods, wire bondless, going away from wire bonds because we're trying to switch a 10 kV device at, say, 15 to 20 kilohertz. Switching that much voltage at that frequency, it's not what you do in silicon typically. And as a result, you've got to make sure that you have very few parasitics. And then, of course, looking at 3D architectures. How do we begin to stack architectures to eliminate wire bonds? So here's some examples of some circuits we've done: matrix converters, non-traditional layout, where we account for the circuit topology in the layout, okay? So these layout methods are first done by hand and ultimately done by a tool, but first done by hand, accounting for what are the different modes of operation of the converter and what sort of devices need to be coupled together very intimately with low parasitics when we do the layout. So that's how we end up with a non-traditional layout. Another one you see here laid out quite differently, okay, as a result of taking into account the type of circuit architecture and where current will flow and under what switching modes, okay? So these are the kinds of circuit-aware layout problems that we now have to begin to deal with as it relates to higher frequency operation. If you take a traditional silicon layout where everything is laid out in a row and you use this in a wide bandgap, I can assure you your power modules will fail. As you increase the frequency, you will not fire the devices all at once. Some devices will turn on before others. You will stress those devices and your lifetime will plummet and you will destroy the devices, okay? Silicon packaging simply will not scale for the frequencies we care about for silicon carbide. We've proved it time and again. And here's an example, okay? If you're gonna build these electronics and you're gonna put these high DVDT and DIDTs through them, you're gonna blow up devices, okay? And we've done it for years, and we've learned our lessons. And so the point that I would make is, from that, this particular destruction was purely a function of a poor layout. Very good circuit design, simple H-bridge, simple design. But the layout had too many parasitics, and it simply would not operate at 100 kilohertz. It operated at 50, it would not operate at 100 kilohertz. The noise was created, coupled back into the gate driver, and crowbarred the power supply and destroyed the module. Okay? Simple as that. Too much noise. So, how do we mitigate those problems? This gets to the emerging trends. This is what we need to begin to start looking at. We need better gate driver ICs. We need better driver circuits that are more immune to this type of issue. We also need better protection circuits that are also integrated, okay? These may be silicon, depending on the temperature rating, or they could be silicon on insulator, they could be silicon carbide. What we're doing is all silicon carbide. And then something all of you need to be paying a close attention to is better layout. One of the things that is very common when you design an integrated circuit is you lay out the circuit and then you do a back annotation of parasitics. You do a full analysis before you go build it. In power electronics, it's not traditionally been the case that we would go do a full analysis before we build the first board. We just go build the board. Won't work. The full analysis we need to be doing is an extraction and evaluation of all of these parasitics. And the reason that I know that you don't do this is because there's no tools to support it. There are no design tools to support a full analysis of the boards and pull the parasitics back in. That's why I know you don't do it, okay? Because there are no tools to make it happen. And this is one of the gaps that we have right now in this field, is a better round-trip engineering of physical design, the physical design of our power electronics, not the electrical. I'm not talking about simulating with a circuit simulator or MATLAB. I'm talking about simulating the actual physical footprint, okay? Much like we would do in an integrated circuit. So what I'm going to do is talk about some of those design flow considerations and give you some examples of some of the circuits that we've done, and then talk about this design automation bit, okay? So most of you would agree that as we start getting into more and more complex systems, our designs are model-based. It may be system-level modeling, MATLAB, it may be, different types of models that you create for your system, but your systems are model-based. And you follow a flow that allows you to do successive analysis, whether it's of the control algorithm, maybe in a MATLAB type of environment. As you then descend down into it, you may be doing some Plex or some type of circuit simulation, PSCAD, something along those lines, any type of circuit simulator, Sabre maybe. At some point, though, at each point, you've got models of the system, okay? And so one of the keys that this slide is pointing out is we need ways to create those models at varying degrees of complexity. So whether it be at the device level, which is something as like a transistor, okay, or something at the system level, where we're talking about signal processing or control flow or something like that. Well, this tool is something that we've developed that helps us do our models. There's any number of tools you might use to create models, but you need to sort of formalize this flow. And so the flow looks something like this. We start with system requirements. What is it we're trying to build, okay? The functional specifications. Then we have some sort of architectural design. This is where we live a lot. Power electronics guys live right here. We take a set of specifications for a power converter, and we develop the architecture, the circuit topology, the control algorithms. That's the architecture. And then ultimately we break it down and we design the blocks. And then we start doing verification. We do simulations, and we do analysis. We spend a lot of time right here. But what we may not spend enough time doing is going back and verifying the functional specs or the system specs. And even at this level, the physical design is one where we sort of tend to leave a gap. We turn over the design, we do a simple board layout. If the board doesn't work, we do another spin. If it's got too much noise, we do another spin. We start spinning those boards, okay? And sometimes it's trial and error. So an improvement can be had as a result of that. So yes, models do drive the design activity, and through the years we've developed a number of standard models for things like semiconductor devices for, say, the lowest level of analysis here, okay? This is more like at the Sabre or SPICE, LT SPICE level, where you've got the semiconductor models. And so we've developed a number of those models, and in fact, we've even done some of them in low voltage. So in an attempt to do silicon carbide integrated circuits and pair those with power devices, we have developed the models for all the silicon carbide PFET, NFET devices that allow us to do that whole simulation and that whole analysis. So this is actually something that only a couple of groups in the world are doing. And we've actually probably done more than anyone else. In fact, this reticle you see here is the second version of a chip that we developed. This is 20 millimeters by 12.5 millimeters, okay? So this is a big chip. It has about 40 different circuits on it, okay? So this gives you a breakdown of what's on that. So you have an integrated gate driver. It's a CMOS gate driver, variable drive strength, okay? You can sync 8 amps or source 4 amps, okay? All CMOS, okay? So PFET, NFET devices. Digital flyback controller, power supply on chip, phase lock loops, D to A, A to D converters, all in silicon carbide. All of these have been tested to over 400 degrees C, functional, okay? Now I can embed these chips inside my power module, and they can take the same temperature as my power devices. And in fact, I can put them side by side, or I can flip chip them on top of my power device. Because they're a perfect CTE match, there's no induced stress, because they're the same material. They're built in the same type of substrate material. So I have a perfect match between the devices. So I'm not going to have failure due to thermal, okay? In fact, these designs were centered at 225 C. They actually operate better at 250 C than they do room temperature. So they just, because of the mobility of silicon carbide, what you end up with is a mobility, you have carriers that aren't fully ionized at room temperature. And so as you go up in temperature, you get higher mobility until you get to about 225. And then it peaks out, and then the mobility goes down like silicon. So you end up with better performing circuits at 225 and 250 than even room temperature, because the material just works better there, okay? So with all of this capability, I can do sensing, I can do control, I can do protection, I can do gate driving, all in silicon carbide when you look at all the circuits on here. It's everything that you need for power electronics. It's all the things that go around the power device that are right inside the module, right there with your power devices. Okay. So this is definitely an emerging trend. It's silicon carbide, all silicon carbide. And when we say all silicon carbide, I don't mean the MOSFET and the diode. I mean the MOSFET, the diode, the gate driver, the protection circuits, everything is silicon carbide. That's an all silicon carbide solution in my book, okay? Everything is silicon carbide. So here's an example of the gate driver circuit. So I cut that piece out right there. And so you can see that we're getting rise and fall times driving a standard Cree power MOSFET here, which is their 900 volt device, and we've driven their 650 volt device and their 1200 volt device. And we're on the order of 50 to 60 nanoseconds, and then 30 to 40 nanoseconds. And notice the x-axis, that's the temperature, up to 425 degrees C. So you can see it's very stable over temperature, very stable, okay? So these are the big power devices, and what you can see is they're designed as, these are the buffer devices, I'm sorry, it's these devices here, okay? That's these two devices here, and they're cut into slices 2 amp slices. So I can, with the digital code, turn on 1, 2, 3, or 4 slices of the transistor and vary the drive strength, okay, as I wish. So this is a digitally programmable gate driver in that case. So in many cases, this is more advanced than some of the things you'll find in silicon. It's just done in silicon carbide. It's not a difficult circuit to design, okay? It's just more suitable for the types of devices we're driving. It actually has built-in test, so it actually runs through a built-in test to determine whether or not it's yielding. Okay, the first time we built this, we got maybe 1 out of 10 that worked. The second time we built it, we got over 9 out of 10 that worked because we were able to deal with some of the process variability better. D to A converter. One of the things, if you're going to do some closed loop control, is that you're going to have to measure sense signals. You're going to have to convert those and then send them back. And so you need a D to A and A to D converter. And so here again, high temperature operation and 8-bit resolution. So pretty low resolution, but still, the next version that we're doing is about a 12-bit converter. Okay. This one has probably got a bandwidth of roughly 4 to 5 megahertz. But good enough for what we're doing in this case. Sometimes you find the need in particularly automotive applications for CAN bus type architecture or communications. So one of the things we developed was communication circuits. And so this was actually operating, tested at, again, over 400C for Cat5 cable. And again, it's just one slice of our chip. Okay? And then finally, we all need regulators, and so this is a linear regulator that we developed, input voltage range of 20 to 30 volts, and it's putting out 15 volts, because all of the circuits we're dealing with here are 15-volt circuits. And so anyway, just more examples of the work. So what has enabled us to be able to do this? We're using a standard IC design flow, but we didn't have any models, and so we had to develop the physics-based model of this. So what we did is we took BSIM4 from Berkeley, and we added silicon carbide effects to it. And then we gave it back to Berkeley. So now there's a BSIM4 silicon carbide that you can get for free. So you can download that model. Okay, we made the modifications adding silicon carbide mobility, band gap, all the other effects, and some things that were not so obvious, and added that to the model, okay, because you couldn't get there with BSIM4. I don't have the curves in this particular presentation, but the curves just simply, you could not make them fit without the physical effects you needed for silicon carbide. Okay, so let me now transition to the last segment of this, which is the design automation part, and this gets to the layout. Okay, so one of the research projects that we have within the Poet Center, and it started actually as a GRAPES project because our high voltage activity required new layouts. You saw that circular architecture that we did for that 10 kV module. That's not something you would typically see. And so we came up with a tool to synthesize layouts. So basically, if you provide your circuit description, this thing will synthesize a layout for you, just like digital synthesis, okay? So basically, it allows you to explore the design spaces really quickly, okay? Gives you about a solution in about an hour. Uses fast thermal and electrical models, still model-based design, okay? And it uses multi-objective optimization to allow you to manage these trade-offs. This is back to what I was telling you before. There's things for you to consider that get more complex than you can deal with easily. But if you have a mathematical engine that can help you visualize the space, you can come up with some better solutions. You can export these solutions into something like a standard tool like Q3D or SolidWorks. And now we're starting to look at accounting for EMI in the layout itself. So here's how it flows. You start with a circuit schematic, okay? And then you create a layout template, just sort of a stick diagram. It's just a notional layout. This would be a very silicon-based like layout. You select the type of materials. Is it gallium nitride devices? Is it silicon carbide? Is it silicon? Doesn't matter. It doesn't have to be wide band gap in this case. Are you using direct bond copper, direct bond aluminum substrates, low temperature co-fired ceramics? What kind of materials? All the material properties are built into the tool. You just have to pick which ones you're using in your stack up, okay? And then you basically select those types of components, And then you assign some performance measures. These are your objective functions. Am I trying to minimize gate loop area, loop inductance, power loop inductance? What am I trying to minimize? Okay, what is the temperature, the maximum temperature that I want to allow? Some of these types of concerns. Thermal objectives, electrical objectives, both, okay? Then you perform the layout optimization. So the engine goes off and it starts coming up with solutions and produces a Pareto front of possible solutions against your performance measures. And you can export the solutions. This process runs in about 30 minutes, okay? About 30 minutes, and produces this Pareto front. And every time you click on one of these solutions, you get a layout of your module, okay? It supports both the 2 and 3D data visualization. So let me show you an example here. This example, this module here, we exported it to SolidWorks, and then we did a full electrical and thermal validation of all of the temperature and the current flow and everything, and the parasitics, all in SolidWorks and Q3D, before we then went and built it. And let me show you how it performs. So this particular module is one that we developed in 2009, and it also won an R&D 100 award. It was a design for electric vehicle motor drive, and there was 3 of these modules required. So this is one switching leg, and you needed 3 of them. This particular device is maybe 3 inches by 5 inches, okay? And this module took 13 weeks for us to lay out. Iterative design, trial and error. You build one, you test it, you build another, test it, okay? This is when we began to discover in 2009 there must be a better way, okay? This is not going to work. This one was meant to operate at 500 kilohertz, okay? Our target was 1 megahertz, but we eventually had to back off, okay, and stick with a lower frequency. Okay, so remember, here's the Pareto front that my tool produced. Now this was done later in about 2013. This was the original design here. These 2 lie on the Pareto front. You'll notice there's only, look at the difference here. Trace width is different, okay? This is a constrained optimization, so these 2 stay the same. Notice the different sizing. It's the busing. The busing is different. The busing impacts the parasitics. And at these frequencies, it impacts the parasitics a lot. So it doesn't look very significant, but indeed it is significant. And our original design, not even on the Pareto front. Now, here's my point. In 30 minutes, I got to these 2 designs. 13 weeks to get to that design. Which would you rather do? And I'm not replacing the layout engineer. I'm just giving him a better starting point. In 30 minutes, I can give that person a better starting point, and then they can go optimize the design even further. Okay, so it's not replacing the design engineer, but in fact, it takes the power electronics engineer, gives you the power to develop this layout for someone who's then going to build it. And you have insight into the layout that you didn't have before. You know where the parasitics are. Now let's take it to the next step. Now that I have the layout, I can extract the parasitics, put it back into my simulation, rerun the simulation, and see what impact those parasitics will have on my waveforms. Not something I can easily do today. This will do it automatically. It creates the new net list for your circuit. You put it back into Plex, LT Spice, whatever, rerun the simulation, see the waveforms. Make a change, do it again. You do the iteration without building the module, okay? So, you look at the data here. I mean, the thermal model, 10,000 times faster than FEM, say Q3D. Parasitic model, that's actually wrong. It's within 5 to 10% accurate because we've improved it, and it's 1,000,000 times faster. This is just, these models run really fast, and they're in an optimization loop, okay? And so these 2 fast models, they allow for the multi-objective trade-off, and then of course we can look at the design trade-off. So where does all this take us? Okay, so we have this, device modeling, IC design capability, this model-based, heterogeneous integration techniques. They're all accounted for in this multi-objective layout synthesis. Where does it all take us? Where are we going with it? Well, let's have a look. So here's a 3D wire bondless half bridge with an integrated gate driver. And now you begin to see how we're putting things in a 3-dimension. We start putting our power devices and our gate drivers on opposite sides of the board because we make that board thin, and now we have a very tight loop. Okay, very, very small gate loop, very small power loop. I can put my decoupling capacitors right here, all on that one substrate, okay? And I start looking at that. And now I can make that back to back. I can stack those if I'm clever, okay? So this is something we've actually built. We can start looking, and we start looking at high powers. This is a collaboration with Arkansas and C. Jang University where we put microchannel cooling. You can buy microchannel cooling substrates right now commercially. They're available, okay? So this is not something you have to build custom. You can buy them, okay? These types of things can be put in. As I start stacking things in 3 dimensions, I can have cooling inside or I can have cooling on the outside. So these are microchannel heat sinks on the outside, okay? So this is actually a replacement for a press pack module. So we're actually going up to 10 kV with this type of arrangement. Then finally, the flip chip power MOSFET. So one of the things that we've done is we've created, and you can see that in the footprint here, you take the power MOSFET that would be inside a TO247 package, take away the package, you flip chip that guy, so you have solder ball connections bringing the backside contact to the front. So this is your drain connection, and here's your gate and source connection on the top. And then I can begin to arrange these devices very closely. I can put them on 2 sides of the board. I can have a very high power density solution and begin to deal with these devices really without the intrinsic package. We'll put them in module. I can parallel these devices and share current with them much more effectively than I can using a package like this, okay? So as we start going to higher and higher currents like 400 amp, 800 amp modules, I can use this type of arrangement with very low parasitics internal. Plus, because it's so small, I don't have to arrange them in a row. I can arrange them in circles. I can do all sorts of different geometries inside the module to promote current sharing, okay? And the layout synthesis tool will be able to do these layout geometries for you, okay? So here's an example of the flip chip, okay, where we're going back to back with the power devices here, okay, and you've got a gate driver off to the side, okay? But you can also imagine putting the gate driver on the other side of the power device. So there's many arrangements that we can think of now. We've opened up a lot of possibilities. So some of these enable the double-sided cooling, enabling 3D integration. And of course, if I have different die heights, then of course this method I can equalize the heights. So I can planarize things. So this is some of the possibilities as we start moving toward more advanced integration. So we actually did this, and one of the things that you discover is you end up with lower conduction losses just by simply eliminating the package, okay? And so, you know, you've got a wire bonded example, which is here, and a flip chip bonded example, which is here. So we're starting to eliminate, you know, sources of resistance just by eliminating wire bonds and things like this, okay? So it's just a better building block to start with, and it promotes this high power density. And then, of course, as I said, taking into account the vertical looping as opposed to putting everything laterally on a board, think in the 3rd dimension. You start putting things on both sides of the board, my power loops get much tighter. My inductances go down. So I can get parasitics that are sub 5 nanohenries, and routinely, I mean, this clean waveform, this blue waveform, is a result of, you know, just doing a better layout. It's just a better layout. I have less noise on my signals. Okay? And these are actual results, you know, operating at the 300 volt level in this case, but we've taken it to very high voltages. Okay? So again, layout is having a big issue as we're promoting higher frequency switching. And then finally, once again, similar result where we've got the wire bondless silicon carbide driver with the integrated gate driver. So in this arrangement here with a very, you know, large board just for the sake of you know, showing it off, you can see very fast turn-on times, faster than the ones that I showed before, even 28 and 20 nanoseconds respectively, 17 and 24 volts per nanosecond, so very high DIDT, DVDT, and very clean waveforms. Okay? And this is just a result of eliminating parasitics, and I can switch this thing as fast as I want now. Okay? So this is where it's taking us. Very high efficiency, very low noise. Okay? As a result of that, we can begin to pack these things very tightly. And with the new circuit architectures that we come up with as power electronics engineers, we can spread the heat based on the topology itself. We won't use a standard H-bridge maybe anymore. We may use a few more switches just to spread the heat because we're accounting for both the electrical and the thermal. You know, it's kind of counterintuitive. You think if I add devices, maybe my reliability goes down a little bit. Not if your fundamental building block is very reliable. Think in terms of an Intel microprocessor, over 1 billion transistors. I don't think reliability is their concern. I don't think adding another 100,000 transistors bothers them at all. We're going to get to that point. This industry will get to that point where we don't care about adding more transistors. It's about signal processing, power processing. And if a few more transistors made in a reliable way allows us to process the signals that look like this, as opposed to the chattering waveforms, that's what we care about. So it won't be about part count, okay? Because our fundamental building blocks will be highly reliable, and that's what we're focused on. And our layouts will be highly reliable. And this is why we need tools to help guide our thinking. Not to replace us, but to guide the thinking so we get better insight into what is better and better and worse, okay? Okay, so my last slide. So certainly, high-speed switching of wide bandgap technology, and it offers some great advantages. It's been demonstrated many times over by many groups around the world, okay? But it comes with some penalties if you don't carefully deploy it, okay? Heterogeneous integration, I think it's required to unleash the full capability of silicon carbide devices. If we pay more attention to this type of activity, then we can really unleash this performance. Issues with things like EMI and signal integrity, they can be addressed through both circuit solutions as well as integration solutions. The two working together is where we have the magic. That's when we have really good innovation. And finally, I think design automation tools like this layout tool and other types of tools, they're becoming more of a necessity. Like we see in the VLSI and the IC design world, they can't build circuits without their tools. Their tools give them the insight to know that things are going to work when they build them. We need those same kinds of capabilities so we have that confidence when we go manufacture something, it will work. And so it's becoming more of a set just because we're going to these higher speed power electronic circuits. Our world is becoming a little more RF-like. We're starting to see more RF type of behaviors in EMI, and because of these high-speed edges that we're producing, we see those impacts. And if we can deal with them, then we'll be okay. All right, so let me stop there. Thank you very much.